Hello, this is Mr. Doro. Today I'm going to introduce you to some properties of gases. You're going to want to have something out to take some notes today because as we go through these properties, you'll want to write some of them down. This picture of this hot air balloon on the front right here is powered by gases. It's full of gases and it is able to lift because of it changes of some of the properties in the gases inside. You're going to want to familiarize yourself with the kinetic molecular theory, which I've called the KMT. In the chemistry book, it's on page 385. In the honors chem book, it's on page 329 and 330. But you don't have to write down everything on each of these slides. I'll underline the important stuff that you should be writing down. But the kinetic molecular theory, kinetic means motion, molecular means dealing with molecules, and theory means that all the evidence points to this, is based on the idea that the particles of matter are always in motion, they're always moving, and that ideal gases, something called ideal gases, perfectly fit all the aspects of the kinetic molecular theory. But the tricky part is that there are no such thing as actually ideal gases, but they act ideal, and we'll talk more about that later on. There are 5 assumptions of the kinetic molecular theory, which are found on those pages that I gave you in the book that you're going to need to know. So you're going to want to write these down. The first one is that gases consist of large numbers of tiny particles. So a whole bunch of these tiny little particles, and they're far apart relative to their size. So they're really tiny, and so comparatively to each other, we're going to say that they're far apart. They do collide with each other, and all these collisions of these are elastic, which means that there is no net loss of total kinetic energy. That means that energy between them is transferred between each of the molecules as they collide with each other. The particles are in constant motion, so they're always moving around. They're not attracted to or repulsed by each other, and the temperature depends on the average kinetic energy. Kinetic energy is the energy of motion, so the faster they're moving, this is the formula for kinetic energy. This is 1/2 mv squared. This should be a squared up here. And so m is the mass, v is the velocity. So the faster they're moving, the greater their kinetic energy is, and the greater the temperature is going to be. Also, if they're moving at the same speed, the more massive one is going to have the greater kinetic energy, and then the greater the temperature is going to be. So the temperature and the kinetic energy are directly related with each other. As the temperature goes up, they move faster. As the temperature goes down, they move slower. As they move faster, the temperature goes up, and so on and so forth. Gases have some unique properties. One of them is that they expand to fit their containers. So whatever container they're in, they will stretch out, and that will be the actual volume of them, and they will spread out as much as they can. They're fluid, which means that they flow, and we think of fluids as liquid a lot of time, but gases are also fluid. They will flow past each other. They have low density, which means that they're spread far apart from each other. They exert pressure, and pressure is when they push out on something. And we know what pressure is when somebody pushes on us. They're putting pressure on us. We have gases putting pressure on us each day. They're compressible, which means you can squeeze them together. That's something that's unique to gases. Liquids are not very compressible at all because the particles are close together already. But because gases have a lot of space in between them, then we can push them together and we can have compressed gas, and that builds up more pressure. And they go through diffusion and effusion. Diffusion is when gases, since they have their random motion, they will spontaneously mix with other gases, and so they'll equal each other out because they're moving around so much. Effusion, again, because they're moving around so much, they'll be bouncing around, and they can go through, if there was a tiny hole in the container, they would end up finding their way out of that tiny little hole. There are some characteristics of gases that can vary, and they're called variables for gases. So one of them is the volume. We can change the volume of a gas, and it's important for us to know what units of volume are. Units could be liters, they could be milliliters. This is centimeters cubed, that's a cubed right there. This is decimeters cubed. So all those can be changed for the volume, and you can change the volume of gas by either expanding it or compressing it. The pressure can also be changed. Pressure is a P, but the units are atmospheres, ATM. This is millimeters of mercury. This is torr, Pascal, and PSI. There's also something called kilopascal too. Temperature can be changed for a gas, and the units for temperature must be in Kelvin. And this is the way that you find Kelvin. You're going to want to write this down and put a little star next to it when you write it down, because Kelvin is found by the degrees Celsius. If you're given degrees Celsius for a gas, you have to change it to Kelvin by adding 273 to it. We're just going to call it 273. It's actually more than that, 273.15 something or other, but we're going to call it 273. And then also the number of moles is something that you can change for a gas. The only way that you can change the number of moles is by either adding or subtracting, taking away gas. If you add gas, then you've added to the number of moles, or let's get rid of that S. Or if you subtract some gas, take some gas away, you've got less moles of gas. So that's actually the amount of gas that you have in there. These are 4 variables that we'll be dealing with. So as we talk about pressure, here is a description of what pressure is. It is a force per unit area on a surface. And so the bigger the surface, the bigger the area that you have. Even if you have the same amount of force, if you spread it out over a larger area, it's less pressure. If you have a force on a very small area, it's going to be greater pressure. So the question I have here is, which shoes would you rather have step on you and why? So here's a pair of shoes that you can see on the top right here. They're spread out. You're going to have the pressure on these areas. This pair of shoes right here, which is like, a pair of prom shoes or something. And by the way, Molly is looking for a prom date. And so if anybody, wants, you can talk to Molly, and she's looking for a prom date. But anyways, here is the pressure on these heels, which is, I believe these are called stiletto heels. I think I learned that. You're going to have the pressure on this small area here and on that heel. So which shoes would you rather have step on you and why? You might say neither. You'd be smart if you said that. But obviously, where the pressure is spread out over a greater area, it's not going to hurt so much. In fact, if you think about these shoes right here, these stilettos, and we sharpen these up so that they have a point on them right there, then definitely they'd end up going right through you, because you're putting even more pressure on a very small area right there, even if it's the same person with the same weight stepping on you. We have gases pushing on us every day in the atmosphere, and one way to measure that pressure is with something called a barometer. A barometer is a sealed tube, and it's in a liquid, and usually that liquid is mercury. In this case it is. It's open on the end down here in the bottom, and atmospheric pressure, as it rises, it pushes down more and more on this container of mercury and pushes it up higher and higher until the weight of the mercury that's pushing down here is equal to the atmospheric pressure. So the higher the pressure, the higher this mercury rises, because more weight needed to equal that pressure. As the pressure drops, then the mercury level ends up dropping, because it will only support the amount of weight that is equal to the atmospheric pressure. So when it asks here what happens at higher elevations, well, at higher elevations you have less air in the atmosphere above you, and so it's going to be lower pressure, and so the lower pressure would be a lower amount of mercury. That changes your cooking habits and all kinds of information like that. For more information on the barometer, you can read that in your book on how that works. Sometimes we have a gas that's trapped inside of something, and we just want to measure the pressure of that gas, and we can use something called a manometer. A manometer sounds like that thing on the Muppet Show, manometer. But manometer does the same thing. Usually you have a column of mercury, and you open it up, and it's kind of like a U channel right here of the mercury, and it will, the higher the pressure of the gas, it will push more mercury up so that it supports the weight of that mercury. The way you find the pressure is you subtract the difference from this level right here, where the mercury is on one side, to the level of the mercury on the other side, and that tells you the pressure. That's just how you measure for an enclosed gas. Now, every once in a while, you'll be given a pressure in one unit and asked to change that pressure to another unit. These are the pressure conversion factors. You're going to want to write down this chart. You're going to want to write pressure conversion factors, and then all of these are equal to each other. So when you write it out, you might want to write equals in between all these, and this one is an equals also, but 1 atmosphere is equal to 760 millimeters of mercury, which is the same as 760 torr, which is 101.325 kPa, which is kilopascals. This is 1.01325 times 10 to the fifth. That is to the fifth. When I copied this over, it didn't come out right. Pascals, we don't use that one very much, so might as well not even write that puppy down. And then 14.700 psi. This is what we use here in America a lot, pounds per square inch, psi. So all those are equal to each other, and we can convert because these are conversion factors, and we'll practice that in just a second. Here's another thing that you want to write: standard temperature and pressure. It's called STP. Okay, I want you to put 3 big stars next to this one. Standard temperature is 0 degrees Celsius, but remember, with gases we don't use Celsius, we use Kelvin. So 273 Kelvin, and standard pressure is 1 atmosphere. So that's standard temperature and pressure, and later on I'll be saying things like, hey, convert that to standard temperature and pressure. You may say I don't have any numbers for that. If it says standard temperature, 273 Kelvin. Standard pressure, 1 atmosphere, and I'll just say at STP. So pause this and write those down. I'm going to go through a couple conversions for pressure for you using that chart that we just went over. So if it gives you PSI, 13.197 PSI, and convert it to kPa, kilopascals, then what we're going to do is one simple little action line, 13.197 PSI. And then we're going to change that PSI. I'm going to bring that down here, copy down. We can change it directly to kPa using our chart from before. Because our chart from before says that for every 14.700 PSI, there are 101.325 kPa. And now PSIs cancel out, and we get 90.965 kPa. Kilopascals. And the reason I went so far is because of my sig figs. The next one right down here, 835 millimeters of mercury, we're converting that to atmospheres. So again, we start out with what we're given, 835 millimeters of mercury. And going down here, we're going to put millimeters of mercury. And up here, atmospheres. Our conversion factor chart says 760 for every one of these. Now that's exactly 1.000. This is exactly 760. And so we do 835 times 1 divided by 760. And I got 1.09868, so on and so forth. And in 3 sig figs, that is going to be 1.10 atmospheres. And so if we need to convert between these two, then or any pressure units, then we just use that chart from before. And here's one that I want you to practice. I've given you the answers, but I want to see the action line set up. A weather report gives a current atmospheric pressure, a reading of 745.8 millimeters of mercury. Express it in atmospheres, torr, kPa, and PSI. I've done the atmospheres for you there and got 0.9813. And then the rest of them, the answers are right there. Make sure you set them up and see that you get those answers. You really need to be reading this information in your book in chapters 13 and 14 or 10 and 11, depending on which class that you're in. And we're going to be talking about gas laws next. So once you get to the gas laws, you can stop or you can get ahead on the reading. Have a great day.